Good day, I'm Dr. T and welcome to my office. So today we are finally jumping into the wonderful world of chemical reactions. Like everything else in this series, or really the whole, all the videos I'm doing, I want to dive in deeper than what you'll need to do so with your students because once again, you need to know a little bit more than what your students will. But this one I want to also address a pretty serious misconception I keep seeing coming up. And I think it is one of those that's actually like baked into the way we teach one of these topics. So I want to directly address this with you all. So one of the key standards that you will see in early and middle grades education with respect to chemistry is this idea of distinguishing between physical and chemical properties as well as physical and chemical change. So obviously I'm going to talk about that, but there becomes a fairly major misconception that I think is baked into some textbooks that I really want to address here. And you, of course, have already seen a preview if you've seen my other videos in the chemistry part of this series, because this is one of those things for me. Okay, so the general idea is a physical property is something you can observe without changing the substance. A physical change is changing the form of a substance without actually changing the chemical it is. So basically, we have not done chemistry. The classic examples would be something like color or weight for a physical property, and a physical change might be melting or cutting. With respect to chemical properties and chemical change, you can only observe the property by changing the chemical, and if you change the chemical from one chemical to another, you're doing a chemical change. And you'll see, telltale signs. You've created a new chemical. It's a different color probably, although there's actually a lot of nuance. There's a lot of different ways to get color. Changing the chemical is actually one way of doing it. There are physical ways of making color that keep it with the same chemical. So a lot of nuance in this topic. But you get the idea of you've changed colors. It's now a completely different state of matter and you haven't tried heating it up. But of course, if you heat up water, you change the state of matter. So this is one of those where there's a lot of nuance, and a little bit of nuance is good to convey to young learners. It gets harder when you're trying to convey a ton of nuance. So obviously you have that nuance here, but I want to emphasize that you never want to teach something that's wrong, because if someone learns something that's wrong, they build a misconception. In order to learn what is true, they must first unlearn what is wrong, and then they learn what is true. It is a lot harder to fix a misconception than simply to add correct information in. So avoid misconceptions whenever possible. Be open and honest that this is a simplification and it's more complexity going on. Otherwise, you either get a student who holds tight to the misconception, or they start thinking you were lying about everything. It's like you weren't lying, you were just oversimplifying. So we want to make sure we do bake in some degree of nuance. Children can handle more than you think. They can handle at least some nuance. Maybe throwing everything at them is maybe a lot, but they can handle some nuance. Here's the part that I see the misconception that's a ton, and I'm quite certain it comes from this complete lack of nuance and the examples we pick. Quite often it is said physical changes are reversible, chemical changes are irreversible. That is an absolutely incorrect statement on both accounts. Physical changes can be reversible. If you take water and you heat it up, you will get steam. If you cool the steam down, you'll get water. That's perfectly reversible. If you take a 2x4 and cut it, that's not going back together again. There's a reason the skilled trades have this saying, measure twice, cut once. Once you've cut, you've committed. So in the case of a physical change, cutting is a physical change, and it is irreversible. Likewise, in chemistry, all chemical reactions are actually reversible, some way more so than others. The showy, the flashy chemical reactions that we like to show, like this thermite picture behind me, or the steel smelting picture far behind me that you can't see due to my big head, those are pretty straightforward one-way reactions. The steel smelting a little bit less so than others because you all know rusting. But there are many other chemical reactions that are very much two-way. If you look at biological systems, I'm a biochemist, so of course I'm thinking biological systems. The vast majority of the chemical reactions enzymes do are completely reversible, and the way cells handle chemical reactions is very different between a very reversible versus a very irreversible reaction. So you do have irreversible or effectively irreversible chemical reactions, but you also have a whole multitude of reactions that are incredibly reversible, to the point where if one chemical becomes another, it will then revert back to the original chemical, or we could say the reactants turn to products and the products turn back to reactants, and they will stabilize at a fixed ratio if left undisturbed. We call this an equilibrium. And this is to the point where you basically can't have just the reactant or just the product under normal circumstances, because if you try and isolate one, it will convert itself into the other. These are very much reversible. So the idea that a physical change is reversible is wrong. It may be reversible, but some of them aren't. And the idea that a chemical change is irreversible is also wrong. Some of them are functionally irreversible, but many are very reversible. So let's make sure we address this when we're teaching and remove this misconception. This does no one any favors, simplifying it to the point of being literally just wrong. Okay, now that my rant is aside, let's start talking parts of a chemical reaction, parts of the chemical equations, and let's dive a little bit deeper. That way you've got a foundation deeper than what you're trying to teach your students. Okay, so I'm going to put up a chemical equation over here. This one I sketched up quick in Inkscape. And so this one is going to be carbonate reacting with an acid to give CO2, water, and in this case it's calcium carbonate, so calcium chloride since the acid's hydrochloric acid. Now, this is actually an interesting one. If this is done outside of a sealed container, this is very much an irreversible reaction because the gas escapes. Carbon dioxide is a gas, so it's going to escape. But if you seal this into a container, it's a lot more reversible. And this one will actually form an equilibrium. Editing Dr. T here, I need to add just a smidge of nuance. This reaction actually happens in about 3 steps, and some of the steps, specifically the last one, is a lot more reversible than some of the early steps. So this does become an equilibrium, but it's not necessarily an equilibrium as shown. Okay, so let's look at the parts. The left-hand side of the reaction, that's the before side, that's the reactants. The right-hand side is the products, and that is the after part of the reaction. These are the same atoms, and this is one of the areas I like to kind of definitely push because it's easy to think that you've got the reactants and the products and they are different things. They are not different things. They are before and after. The reactants react to form the products. They become the products. The exact same atoms that you have on the reactant side are the exact same atoms over on the product side. Okay. Now, we can put a bit more information here. The arrow, we call that a reaction arrow or the yield arrow. It's pronounced yield, you can read it. The plus signs that add up each of our molecules or formula units. Remember, a molecule is a discrete clump of atoms. A formula unit is the smallest ratio of a lattice. So the calcium carbonate, that's a lattice, that's a formula unit. The hydrochloric acid, that is a molecule, so that's actually a chlorine and a hydrogen, and they're stuck together. So the plus signs between them, those are pronounced and. So I would read this off, calcium carbonate and hydrochloric acid react to yield calcium chloride and water and carbon dioxide. Normally you don't just read them off. I mean, that was pretty clunky. Okay, so that is one feature. Now we can put on state symbols at the end of them if we want. These are optional. So the S is for solid, the AQ is for aqueous or dissolved in water. By the way, reactions do not have to take place in water. They can take place in other solvents or in a solvent-free environment. The thermite picture behind me, I maybe just had to put it up here. The thermite over here, this one is a solid phase reaction. You've got iron oxide and aluminum powder, fine powders. They react together to yield aluminum oxide and iron liquid. So a lot of reactions are aqueous, a lot of biological reactions are aqueous, but you don't need to be aqueous. Okay, back to the original one. So S is for solid, AQ is for aqueous or dissolved in water, L is for a liquid. Note, you'll notice the water is a liquid, not dissolved in water. It's kind of one of those meta things, but no, the water, we treat that as a liquid. If you dive into equilibriums and them going back and forth, that's actually is relevant. We're not doing that though, don't worry. And then the carbon dioxide, that guy's a gas, he gets a G. So pretty straightforward, kind of what you would expect. The aqueous is the only weird one on the list. And then you'll notice a couple of numbers floating around. These guys are coefficients, and they're telling you the number of molecules or formula units in that reaction. Because keep in mind, this is before and after, so you have to have the same atoms, and you're looking at a ratio. So everything we're doing here is ratios. I like to jokingly say, only half jokingly to be honest, that especially the first semester of a general chemistry course, it's basically, ratios 12-11 kind of thing. It's like, it's a chemistry class, but it's a ratios class. Half the class is ratios. And so what these larger numbers out in front, they're saying what ratio of each one of these formula units or molecules are involved in this reaction. And then we can use those ratios to calculate, well, how much of one would I need to react with how much of the other, and so on and so forth. Okay, I'll switch this up for a different one. This guy is an equilibrium reaction, and as such, it's got a slightly different arrow. So the effectively one-way arrow is an arrow. It's a line with a two-headed barb pointing from the reactants to the products. Whereas an equilibrium arrow, it's two half arrows. It's two of these single barbed arrows, one pointing one way, one pointing the other way. And this is really being very clear that this is a reversible reaction. The previous arrow, that is more of a generic. That's just kind of the standard one we write. But this one, we're being very explicit that this is a two-way reaction. Now, you'll notice if you count up, you multiply each one of the formula units by its coefficient. So if I look over here, I've got the hydrogen gas, so that's two hydrogens stuck together, and I'm saying there's three of those. That would be 6 hydrogens. So I do that on one side, and that would be the reactants for this one. This, by the way, is the Haber-Bosch process, where you're fixing nitrogen to form ammonia, which can then be used for fertilizer. It's actually an absolutely critical reaction for an society level, economic level. It's where we get about half our fertilizer from. Kind of a big deal. Anyways, so you see you've got 6 hydrogen atoms on one side. Now this is a ratio, so you don't actually do 6 hydrogen atoms. You do a whole lot more. But you would do, for every 1 nitrogen molecule, which is 2 nitrogens, the 1 isn't written, it's just implied. So if there's no coefficient, it's assumed 1. Then you got your 3 hydrogen molecules, which each have 2 hydrogen atoms. So you have 6 hydrogen atoms. And that's going to give you 2 ammonia molecules on the product side. So those 4 molecules are going to smash together, and you're going to get 2 molecules out. Each one's got a nitrogen and 3 hydrogens. Well, if you run the math, you start out with 2 nitrogens, and you get 2 nitrogens just arranged differently into different molecules. You start out with half a dozen hydrogens, and you're going to get half a dozen hydrogens when you're done. So you're always getting out what you put in. You don't have an atom magically appearing out of nowhere. That doesn't happen. You don't have an atom magically disappearing into nowhere. That doesn't happen. If you're doing some nuclear physics stuff, you can lose mass, but in chemistry, we're not dealing with energy levels that involve losing mass. That goes by E equals mc squared. We're not really going to go for that. But let's just say in 1955, the United States converted 1 kilogram of lithium to pure energy on Bikini Atoll. It was a mile-wide crater. Yeah, we're not getting rid of matter here. We're not converting matter to energy. Chemistry does not work at these magnitudes of energies. Editor Dr. T here again with another freeze frame of disappointment. I forgot to mention above and below the arrow, we will sometimes put extra information, other chemicals or reaction conditions that are involved with the reaction but are not necessarily part of the reaction. So this would be something like heat, which we can indicate with a triangle. In this case, I've got a catalyst going on. Or you might have solvents or other information there that's not part of the reaction but is involved with the reaction. And here's another picture from Wikipedia, just kind of highlighting this. This is combustion of methane. So I've got a methane, and this was got kind of highlighting the atoms here. So I've got methane. I've got two oxygens. Each one's a pair of oxygen atoms, and that's converting to CO2 and water. So you get the idea. This is balancing. This is giving me a nice ratio here. This is important because now we can figure out how much of one you need to react with the other, and you can start doing chemical accounting, which is known as stoichiometry. Okay, so when a chemical equation is set up proper with coefficients, we call that balanced, and we can jump into stoichiometry. We're not going to cover the math in this course for stoichiometry. Feel free to take one of my full-on chemistry courses if you want to do that, or peruse Crash Course Chemistry. Hank Green does a decent job. But I do want to point out this idea of a limiting reactant. So if I am going to do this, I can figure out how much chemicals I need. And if I put in the right amount of each chemical, that I use just enough. We call that a stoichiometric ratio. And that's great. And they both reactants will use up at the same time, and I'll get all my products. Unless it's in equilibrium, in which case I'll get an equilibrium going on. But if I put in too much of one reactant and not enough of the other, then the one that's lacking is going to stop the reaction because it's going to run out. If you're making peanut butter and jelly sandwiches, you got to have enough bread, enough peanut butter, enough jelly, and when one of those runs out, you're not making peanut butter and jelly sandwiches. Same way goes for a chemical reaction. Once one chemical runs out, you can't make more. So the chemical that runs out is what we call the limiting reagent, and any chemicals left over, we call those excess reagents. Now, if it's an equilibrium reaction, you're never going to fully use them all up. You're always going to get that equilibrium, but you can kind of shift it back and forth and kind of tweak it by increasing or decreasing certain chemicals. This is what's known as Le Chatelier's principle. So you can kind of adjust those. If you look into biochemistry, it's all about Le Chatelier's. Once again, Le Chatelier is high school, if not getting into college level chemistry, so we're not going to dive too much into Le Chatelier. While we're talking stoichiometry, we need to talk about units real quick. The units of a chemical equation are individual atoms and molecules. So if I have a chemical equation like this one, well, that's describing the ratio of individual atoms and molecules. But atoms and molecules are obscenely tiny. As I think I've given examples previously, there's roughly, in a shot glass, admittedly a small one, the same number of water molecules as there are grains of sand on the planet. So we need to adapt the fact that we're going to be working with some obscenely large numbers. To do this, we're going to use a counting unit. And you're familiar with counting units already because you already know what a dozen is. So a dozen eggs is 12 eggs. Anytime you would need to use individual eggs, you could just switch everything over to dozens. So I could say, hey, I'm making 8 muffins, and I need 2 eggs to do that. Or I could say, I'm making 8 dozen muffins, so I'll need 2 dozen eggs to do that. Now, we're going to do the same idea. Our unit is the mole. The German spelling is MOL. That's the original spelling. The English spelling is MOLE. Basically, that's the English spelling that we get closest to the pronunciation of the word mole. We are not dealing with small furry mammals here that like to dig. Instead, we are dealing with an Avogadro's number of something. Avogadro's number is going to be this guy, roughly 6.02 times 10 to the 23rd. That's a lot. That's a really, really big number. So why do we have such a random, really big number? Well, historically, and by historically I mean prior to 2019, Avogadro's number was set up to be the conversion factor between the unit of mass we use for the macroscopic world, the gram, and the unit of mass we use for atoms and molecules, the Dalton. Daltons are defined based off of the mass of carbon-12. It turns out that the nucleus of an atom will actually change its mass, not just by how many nucleons are in it, but also how many nucleons are in it. There's this idea of mass defect. So a proton in a hydrogen nucleus is actually going to weigh more than a proton in a carbon nucleus, which will weigh more than a proton in a iron nucleus. So ideally, we would just use the mass of a proton. It changes mass. So we can't just do the mass of a proton. So we kind of ballpark this. We picked carbon-12, relatively easy to utilize. And so we said, okay, 1/12 the mass of a carbon-12 atom. So we're going to include the electrons. That's going to be a Dalton, and that'll be our unit of mass for atoms and molecules and the like. And so we can add up the mass of all the atoms in a molecule or a formula unit. That's our formula weight. We can get that in Daltons. And because Avogadro's number was originally set to be the conversion factor between grams and Daltons, then, hey, if it's, say, 18 Daltons, then that means it's also going to be 18 grams per mole. And it was quite convenient, and that's the way we do the conversion. Now, I was saying in the past tense, 2019 we redefined the kilogram. In the process, we also redefined the mole as just stating it is Avogadro's number. That number was picked to be as close to the ratio between grams and Daltons as was known in 2019. For all practical purposes, it's still effectively the same. That's a really close number to the true value, but you know, as times go by, if you need ultra high precision, a Dalton is a Dalton and a gram is a gram, and they don't directly interconnect with Avogadro's number. Okay, so from this, what we can do is we can weigh something. We know that the Dalton is going to be the grams per mole, so we can use that. It's got two parts. We can do dimensional analysis, and so we can weigh something. We can convert using its formula weight, the weight of the formula unit, and convert that into moles, and because moles are a counting unit, we can substitute those in any place where we would use individuals. So I could take a chemical reaction and I could plug in to one spot the number of moles I have. I could use the coefficients to solve for the number of moles of the other chemicals that I would need or would be producing. Now, a couple of quick points here. One, a lot of students like to start multiplying by Avogadro's number. Now, we're not really going to do any math like that in this class, but if you are, be very wary because generally speaking, we don't go back to individual atoms. It's just too many of them. They're absolutely tiny little things. We work with tons and tons of them. So we just stay in moles. So almost never do we convert between moles to individual atoms. That's a weird exercise that some textbooks will do, and otherwise you almost never actually do that. So if you're starting to be tempted by multiplying by 6.022 times 10 to the 23rd, probably don't. Second, you'll see a lot of textbooks use the unit of mass as the atomic mass unit for our atoms and molecules. And this is one where they're about half a century out of date. The atomic mass unit is based off of the atomic weight of oxygen. It was developed in 1929 and was superseded by the unified atomic mass unit, aka the Dalton, in the 1960s. The issue ended up being is there was a disagreement between the physicists and chemists of whether or not you should count the electrons, and that's before we knew that isotopes were a thing, and thus the definition didn't take into account that oxygen has more than one isotope. During the 1960s, the atomic mass unit was phased out and replaced with the unified atomic mass unit, which is based off of carbon-12 and includes the electrons. Yay, we chemists won this particular round. This was later given the alternative name of the Dalton in honor of John Dalton in 1993. So if you have a textbook that says AMU, it's out of date. It should be U for Unified Atomic Mass Unit or DA for Dalton. Dive into a couple of major categories of chemical reactions, and I've got a picture from Wikipedia over here. Okay, so typically in kind of early chemistry, which is traditionally inorganic chemistry here in the US, UK, they actually start with organic chemistry. Organic chemistry is chemistry of carbon. Inorganic is the chemistry of not carbon, so basically everybody else. Although things like carbonate still go in the chemistry of not carbon because vibes, I guess. Yeah, I didn't make up the setup. There's a little bit of historical vibes-based categorization here, but it kind of makes sense. Okay, so typically we start with kind of these four classifications. Organic chemistry is going to have their own set of classifications. These are very generic, big over-level view things. Keep in mind, everything is a fuzzy Venn diagram here. Okay, so we can have what we call a synthesis reaction. A synthesis reaction takes two or more chemicals and merges them into one chemical. Now, I will say there's occasional synthesis reactions where you take a bunch of chemicals and you actually form it into like two. So it's not necessarily two into one, it's basically many into few. So like photosynthesis, you get sugar, but you also get some oxygen out the back end too. So once again, fuzzy Venn diagram. Decomposition reaction. This is the opposite. So this is few into many. Specifically, it's one into many. So you're going to take one chemical, you're going to break it apart. Famously, pyrolysis is this. So in pyrolysis, what you do is you're heating up an organic material like wood, and then you're breaking it down into simple molecules. This is actually how fire happens. Wood does not burn. The pyrolysis products of wood do burn. This is why you have to use kindling. You got to get the pyrolysis going in order to make the material that actually burns, to get enough heat to do the pyrolysis, to make the chemicals that burn, to get more. You get the idea of how fire works. It's actually insanely complicated. Fire is one of those really deep end topics. Okay, moving down. Next one is single displacement. Generally speaking, you take a ionic compound, so I'll call a salt. It's got a cation and an anion, and then you're going to react it with a metal, or a metal in its metallic form. And then that metallic metal is going to be oxidized. So oxidation is loss of electrons. And the ion that's originally the cation, it's going to be reduced. Reduction is the gain of electrons. So basically, you're going to trade electrons from the metallic metal to the metal cation. So one's going to become what was a cation is now a metal, and what was a metal is now a cation, and you've basically swapped out your metal. So this is a single replacement or a single displacement. I learned it as displacement, but I see replacement used much more these days. The two terms are pretty much interchangeable here. The last of the lot is double displacement or double replacement, whichever you want to call it. And in that case, we are going to take two ionic compounds, so two salts, and we're effectively going to trade cations or anions, either way we want to phrase this. And so if you have cation A and cation C, A is with B, C is with D, well, now A is with D and C is with B. And you're just going to do a quick swap of partners here. And with these four, you kind of generally bracket most inorganic reactions. Organic reactions, they don't play nicely with this mess. So there's a whole nother set that we jump in with organic reactions that are beyond the scope. Now, I mentioned reduction and oxidation. This together is usually what we call a redox reaction. This is a reaction where electrons transition from one atom to another atom. Sometimes it's a full-on clean move. Sometimes it's a little bit fuzzier of a move. So sometimes you make ions. Sometimes you don't actually make ions. This is one of those where things can get a little bit interesting. Now, fun fact though is you got moving electrons. Do you know what else is moving electrons? Take a guess. Did you guess electricity? Spot on. Yeah, we've got the beginnings of a battery. So if I want to do a battery, basically what I can do is take a chemical reaction and split it into two half reactions. I physically separate them. Now, if I've physically separated them, on one side I can do reduction. It can generate an electron. I can ship the electron across the wire, make it do some work, make an electric current. It's always going to be DC, by the way, or direct current. And then it goes to the other side where I can then use it to do an oxidation reaction. Now, I'll have to have something like a salt bridge or a membrane in order to balance out the charges here, because I am moving negative charge and I'm probably generating some cations on the other end. So yeah, I'm going to have to balance out some charges here. All circuits go in a circle, and basically I have to have the last little bit of a circle. Now, if I want to run this in reverse, because remember, chemical reactions are reversible, sometimes this will work better in practice than other times. This is one of those where sometimes reversing them, it doesn't reverse very well. But for some of them, it's pretty easy to reverse. I use an electrical potential, so I apply a voltage, I run the electrons going the opposite direction, and now I am able to reverse everything, and this is charging the battery. So, you notice the lights went dim previously. I had to take some of the batteries off of one of my lights, I think it was that one, and hey, run the chemical reaction going the other way in order to top it up and replace it with a fresh one. Okay, so let's talk briefly about chemical energy. You get a couple of different ways of doing this. This is actually one of those areas where we can dive in pretty deep, but we're not really going to. Okay, when it comes to chemical energy, there's basically kind of two thoughts. What is the arrangement of bonds? If I've got a bunch of chemical bonds, it's always going to take energy to break them. That's one of the myths that usually gets weaseled into biology. It's actually one of those kind of bell curve meme things where the idea is breaking bonds gives you energy. It doesn't. It always takes energy to break bonds, but if you break the right bonds and you reform bonds, you're going to get energy whenever you reform bonds. So if you just make sure you get more energy out than you put in, congratulations, you just netted some energy in an exothermic reaction. It's kind of like buying stocks. You make money if you buy stocks and then sell them for more money. You don't make money by buying the stocks directly. Now, of course, just like stocks, you can sell the stocks, you can buy high and sell low, which will lose you money. And in chemical reactions, you can break fairly energy-intensive bonds to break and then form weaker, less energy-intensive bonds. And in that case, you're going to lose energy. Energy is going to get sucked into it, and that is an endothermic reaction. We also have the idea of enthalpy, which is chaos. If I increase the chaos of the system, I increase the number of possible microstates it exists in, that's actually going to encourage my reaction to go forward. So typically, reactions going forward are either because I'm getting some energy out of it, and the energy is lost, or it's becoming more chaotic, or both. And we can dive into more with that, but I will leave that for Reagent 2 class because the math gets a little bit intense. I do apologize. This video I keep running into, and there's more, but I'm not going to cover that. So I do apologize for that. I'm not going to cover it. I'll let you bug Hank Green or take a general chemistry class, but there is actually a lot here that I'm very much glossing over to keep this video not ridiculously long. I'd like to keep them, a half hour would be nice. I've not succeeded yet. Okay, the last part I want to cover in this video before wrapping things up is talking about reaction rate. What makes a reaction go faster or slower? And what can we do to control that? Okay, so let's think about what has to happen for a chemical reaction. You have to have, generally speaking, two atoms slam into each other. And when they slam into each other, their electrons are going to rearrange. And as their electrons are rearranging, they're going to form new bonds and you get new chemicals. There are exceptions to this. If it's a light-based reaction where it's conducted by photons hitting, well, they don't slam into each other. It's the photons get in and it excites the electrons and they rearrange that way. But either way, we need to add energy. We need to get the electrons to rearrange themselves. This gives us into a transition state. We're transitioning from one form to another. It's inherently unstable. For some of my students, I like to jokingly discuss the bad dating advice model of chemistry. And the transition state could easily be one of those where you're dating two people at the same time. This ain't gonna last. They're gonna find out, and you're gonna lose at least one of them. So when a chemical's in a transition state, it's unstable. It will not last. And the bonds are gonna rearrange themselves. So it takes energy to get up to that transition state. The amount of energy it takes is what we call the activation energy. And then it's going to either go back to the way it was, or it is going to go into its new form. Now, it may go into a new form and then go to a new transition state, in which case that intermediate form is called an intermediate. Wow, the naming is obvious, isn't it? And eventually you're going to get towards your products. But at each point, when it goes up to a transition state, it can go back one way or the other. And you can do an energy diagram with this one if you are so inclined to do so, following the energy going up and down, etc. Okay, so if I want to make it go faster, I give it more energy, because one of the key things that limits this is, well, do they have enough energy? Usually an example I like to give is, what's the difference between a 20-car pileup on the interstate and bumper cars? In both cases, you're in a motor vehicle and you're slamming into your friends. Yeah, the difference is you're probably going a lot faster on the interstate. Speed matters. So bumper cars, I mean, you can outwalk those things. Let's be honest. They are capped at a very slow speed, whereas your car, it can go very fast. And the faster you're going, the more, shall we say, work gets done when you collide. And the same goes for molecules. If they are going very slowly, the electrons simply repel and they bounce off. Nothing happens. Whereas if they're going quite quick, then when they collide, the electrons rearrange and you have a very good chance of getting into a transition state. But this actually adds an extra feature. More energy you have, the more likely they're going to go fast enough and collide. Generally speaking, we're going to have energy in the form of temperature. So temperature, for this class's purposes, can be viewed as the average kinetic energy of the particles of your substance. Now, there are many models of temperature. This is one of the simplest ones. There are more advanced models for other applications. But for this application, we can think of as temperature as the average kinetic energy, aka how fast are they going and how heavy are they. And well, the higher the temperature, the more individuals in your reaction mixture will be going fast enough that when they collide, they'll meet the activation energy. Okay, so make it faster, you can increase the temperature. Likewise, cooling it down will slow it down. This is why refrigerators keep food fresh longer. Biology is chemistry. And so if I slow down chemical processes, I slow down biological processes, like the microbes eating my lunch before I get to it. Now, another way of doing this is to increase the concentration. How many individual particles are in the container within a given space? If we go back to the bad dating advice model of chemistry, is it easier to find a date in the middle of nowhere, Wyoming, or inside of, say, a university setting? If there's a bunch of people who potentially could be the one, it's a lot easier to find the one than if, there's no one in the next square mile. So as such, a chemical reaction, you have to have the two chemicals collide into each other and physically contact. This is totally random, and so you need to hedge those probabilities. The more of them you have, the better your probability of them actually colliding. So I can increase my concentrations, and that way the reaction will go faster. You will notice that if anyone you know is on oxygen, especially if they're on the tanked oxygen, they will almost always have signs around their house saying, do not smoke or light candles or have fire in the house. The reason ends up being is because of the tanks of oxygen, if they're using tanked oxygen, increase the amount of oxygen in the room. They're inhaling the oxygen, but their body isn't using most of the oxygen. They're enriching it because presumably their lungs are struggling to function. So they're exhaling a lot of oxygen. The concentration of oxygen is greater in the room. Fire is a chemical reaction that involves oxygen. The more oxygen in the room, the faster the fire will burn. And things that don't normally burn will start burning, and such. For someone who's on oxygen and they're using tanked oxygen, then their house will have excess oxygen in there, and a small fire can become a large fire very, very quickly, and that is a serious safety issue. Okay, so we can heat it up if we want to go faster. We can increase the concentration. This is why the concentration of acid matters during a safety review. A concentrated acid can do a lot more chemistry a lot faster than a dilute acid of the same type can do. So a concentrated acid has a greater hazard than a dilute acid. Doesn't say the dilute acid is safe, just saying more is more. Okay. Last one I want to bring up is that of a catalyst. A catalyst is a chemical that changes the inner workings of a chemical reaction. The chemical reactions I keep showing you are ones that are just kind of a summary overview. Put A in, get B out. It doesn't show the sausage being made. You put pig in, you get sausage out. There's a whole lot between pig to sausage going on that usually doesn't get covered. And what a catalyst ends up doing is it changes how the chemical reaction works, and thus making it go faster. It generally lowers the activation energy. In the bad dating advice model of chemistry, I like to think of it as a matchmaker or a dating service. A classic example for a catalyst would be an enzyme. Enzyme is able to bind the chemicals that it's going to do the reaction with, gets them close together, angles them in the right orientation, because not only do they have to collide in the proper orientation, so aiming them in the proper orientation, getting them close to each other, hey, that's going to speed things up quite a bit. Okay, so we have covered my rant on physical versus chemical change, introduction to chemical reactions, as well as different types of chemical reactions and what speeds them up, slows them down, etc. in what I am hoping will edit down to under half an hour. I doubt I will have succeeded. So with that said, have a wonderful day, and I will see you in later videos.